Okay, section 1.5, operating system operations. As mentioned earlier, modern operating systems are interrupt-driven. If there are no processes to execute, no I/O devices to service, and no users to whom to respond, an operating system will sit quietly, waiting for something to happen. Events are almost always signaled by the occurrence of an interrupt or a trap. A trap is a software-generated interrupt caused either by an error or by a specific request from a user program that an operating system service be performed. The interrupt-driven nature of an operating system defines that system's general structure. For each type of interrupt, separate segments of code in the operating system determine what action should be taken. An interrupt service routine is provided to deal with the interrupt. Since the operating system and the users share the hardware and the software resources of the computer system, we need to make sure that an error in the user program could cause problems only for the one program running. With sharing, many processes could be adversely affected by a bug in one program. So, without protection against these sorts of errors, either computer must execute only one process at a time, or all output must be suspect. A properly designed operating system must ensure that an incorrect program should cause other programs to execute incorrectly. So hardware provides four kinds of protections. Let's look at them. They are dual mode operation, I/O protection, memory protection, and CPU protection. Let's learn them. First one, dual mode operation. In order to ensure the proper execution of the operating system, we must be able to distinguish between the execution of operating system code and the user-defined code. The approach taken by most operating systems is to provide hardware support that allows us to differentiate among various modes of execution. At least, we need two separate modes of operation, user mode and the kernel mode. User mode, execution done on behalf of a user. Monitor mode, also called kernel mode, supervisor mode, privileged mode, or system mode. Execution done on behalf of operating system. The hardware added a mode byte to computer hardware. Generally, the program status register, that is PSR, to indicate the current mode. If the mode bit equals to 0, it is kernel mode or monitor mode. If the mode bit equals to 1, it is user mode. With the mode byte, we can distinguish between a task that is executed on behalf of the operating system or that is executed on behalf of the user. When an interrupt or fault occurs, hardware switches to monitor mode. So let's look at here. Above this line, it is user mode. Down this line, it is monitor mode. At system boot time, the hardware starts in kernel mode. The operating system is then loaded, and the status and start use applications in user mode. Whenever a trip or interrupt occurs, an interrupt or a trip occurs, the system trap from user mode to kernel mode. That means the hardware changed the mode page from 1 to 0. So the hardware is working in kernel mode. That means the operating system takes control over the system. And according to the interrupt signal, the system will find the interrupt service routine and execute this routine in kernel mode. After finish executing the interrupt service routine, the hardware will change the mode bit from 0 to 1 and then resume the user process just now be interrupted. So the dual mode of operation provides us with the means for protecting the operating system from errant users and errant users from one another. That means if the user cannot control the hardware the user cannot control the hardware in monitor mode. Most services must be done in kernel mode. That means the operating system controls the hardware. Okay, so we accomplish this protection by designating some of the machine instructions that may cause harm as privileged instructions. The hardware allows privileged instructions to be executed only in kernel mode. If an attempt is made to execute a privileged instruction in user mode, the hardware does not execute instruction, but rather treats it as illegal and traps it to the operating system. So the operating system takes control again. The instruction to switch to kernel mode is an example of a privileged instruction. Some other privileged instructions include I/O control, timer management, and interrupt management. The second hardware protection is I/O protection. Just now we already know privileged instructions, and we also know that all the hardware operations must be done by privileged instructions. So we say all I/O instructions are privileged instructions. That means all I/O operations must be done in kernel mode. That means only can be done by the operating system itself. To do I/O, user program executes a system call to request the operating system perform I/O on its behalf. So let's look at this picture. This is the picture for main memory. And you see the lower address part is for resident monitor. That is the kernel part of the operating system. And the higher address part is for the user program. Okay, so at the beginning, maybe one user process is executing on CPU. After a while, maybe he will do the user process wants to do I/O operation, so it will call a system call, such as we will call in our C program, such as printf, scanf, fopen, fread, or fclose, such as this kind of system call. So, and this system call will make the machine trap into kernel mode, from user mode into kernel mode. And the operating system kernel part accept this system call, and according to the parameter it passes, the user process pass, it found that it will read a file. So the operating system control the hardware, maybe the hard disk, to perform I/O operation, to read a file from the magnetic disk. After finish reading, the operating system will change the mode from kernel mode into user mode, then resume the execution of the user process. So you can see from this picture, you will understand that to do I/O, user program can only by system call. It cannot control the I/O devices directly. Okay, so this ensures that a user program could never gain control of the computer in monitor mode. The third hardware protection is memory protection. That means must protect the operating system from access by user programs and protect user programs from one another. In order to have memory protection, the hardware or the machine will add two registers, two special registers that determine the range of legal addresses of a program may access. The first special register is base register, holds the smallest legal physical memory address. And the second special register is limit register, contains the size of the range. So you can see this picture. Let's also describe the memory. It's also described the main memory, and also the lower address end is for the resident part of the operating system, monitor part. And here we can see there are 4 jobs or processes resident in the memory simultaneously. Okay. Now here, maybe here you can see from this picture, we know that job 2 is executing on CPU. So the base register's content is this one, and the limit register content is this one. Okay, that means one job 2 work, when it accesses the main memory, the address must fall into this part. Okay, this part. So let's look at how to protect. When job 2 executing instruction, maybe it will access memory for fetching data or for fetching instructions. So it will generate a memory address, and the hardware will use this address first compared with the content of base register. If it is larger or equal to the base register, it's legal. Otherwise, it is illegal. The hardware will trap to operating system monitor code and will generate an error signal. It is addressing error, and the user program will be interrupted. That will be which will be stopped. Okay, will be terminated. Okay, illegally. And then if the list address is larger or equal to base register, then the second step, it will compile with the result of this, the content of the base register plus the content of limit register. If the address is smaller than it, then it is legal. The address will pass to physical memory and will get the instruction or the data. Of course, here, if the address is larger than the content, it's also illegal and trapped to the operating system monitor, and the operating system will take over control the machine, and stopped and terminated the user program for addressing error. Okay, so you can see, but one point I must emphasize: this scheme is only for contiguous memory management scheme. Okay, this memory protection scheme is only for contiguous memory allocation. As for the patching or segmentation, we will learn in the future. The memory protection scheme is different. Okay. So memory outside the defined range is protected. Only the operating system can use a special privilege instruction to load the base and limit registers. That means to load the base and limit registers are privileged instructions. Okay. The operating system itself, executing in monitor mode, is given unrestricted access to both monitor and user's memory. That means the operating system itself, executed in monitor mode, can access the whole physical memory. So the operating system can load users' programs into users' memory to dump out those programs in case of errors, to assign and modify parameters of system calls. When executing in monitor mode, the operating system has unrestricted access to both monitor and user's memory. Okay. The fourth hardware protection is CPU protection. That means we must ensure that the operating system maintains control over the CPU. Prevent a user program from getting stuck in an infinite loop or not calling system service and never returning control to the operating system. So use a timer. A timer can be set to interrupt the computer after a specified period. The period may be fixed or variable. A variable timer is generally implemented by a fixed rate clock and a counter. The operating system sets the counter. Every time the clock ticks, the counter is decremented. When the counter reaches 0, an interrupt occurs. So when an interrupt occurs, that means, so from this picture we review it here. When an interrupt occur, that means the hardware will trap to kernel mode, from user mode to kernel mode. Okay, that means the operating system itself will take over the control of the system, of the hardware. Okay, so we use timer can prevent a user program from getting stuck in an infinite loop. Okay. Load timer is a privileged instruction. So you know that Also, only operating system can load timer. Timer commonly used to implement time sharing system. The timer could be set to interrupt every n milliseconds. When n is the time slice that each user is allowed to execute before the next user gets control of the CPU. That means each user process is allowed to execute at most each time at most one time slice. When the timer interrupt, even though the user process doesn't finish, and the operating system will get control, and it will schedule the next user process to run on the CPU, and the above user process will be put and at the end of ready queue, waiting for next execution. Okay, so this is time sharing. Of course, we will learn afterwards.